In this lesson, we'll look at the solid state. This will be our final lesson. Okay, here we have platinum on the right, which consists of all of the same type of atom. Here we have an ionic solid, potassium iodide. The potassium is shown in darker purple, and the iodide are the larger particles. The platinum on the right is held together by metallic bonds, whereas the one on the left is held together by electrostatic interactions, ionic bonds. Okay, let's move on to stacking patterns. Okay, in a crystalline solid or crystal lattice, there's a couple of common stacking patterns. These are AB, 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 and ABC, ABC. Okay, the difference here is that here we have AB, where the blue or purple layer sits in the gaps between the atoms in the yellow layer. Okay, and for ABAB, this other yellow layer has atoms which lie directly above those of the bottom layer. Okay, and then for an ABC, okay, it starts out the same. We've got these purple atoms that are in the spaces between the yellow atoms, but then the red atoms here are not directly above the yellow atoms. Instead, they're in the spaces of the purple atoms. The AB arrangement is called hexagonal closest packing. And the smallest unit of this three-dimensional arrangement is called a unit cell. And a hexagonal unit cell is an array of 9 closest packing particles that are the repeating unit in a hexagonal closest packed crystal. Okay, the other common type of arrangement is what's called cubic closest packing, and that's the ABC stacking pattern. Okay, for a face-centered cubic cell, this is an array of closest packed particles that has 8 of the particles at the corners of a cube and 6 of them at the centers of each face of the cube. Okay, so here we have what's called a simple cubic. If we arrange the atoms in a square packed layer like this, and then the layers are directly on top of each other, okay, the unit cell just has the atoms at the corners. Okay, if we have a simple cubic, but then we have another atom in the center, this is what's called a body-centered cubic unit cell. Okay, so for a simple cubic unit cell, if we slice it this way, we'll see this in just a moment. Each corner shares, or each atom is shared by 7 other unit cells. Okay, so this is just 1/8 of an atom. and then there's 8 corners of the cube. Okay, so the radius of the cell is half of the length of a side. Okay, in a face-centered cubic unit cell, okay, here we have atoms at the corner, and then we have an atom at each one of the 6 faces. The face atoms are shared by one other unit cell. Okay, and so the radius is the diagonal of the body, like this. It goes from one corner to the opposite corner, and then we can calculate that using what the radius is, using the Pythagorean theorem for a right triangle. Okay, so this is a diagram that shows, okay, first of all, for a simple cubic, each corner atom is shared by 8 unit cells. So in a single unit cell, that's just 1/8 of an atom. For a face-centered atom, that's shared by 2 unit cells. So in a single unit cell, that represents half of an atom. Okay, so there are 6 faces. So for a face-centered unit cell, okay, we would have 1/2 times 6 faces. That would be 3 atoms. Okay, for a body-centered, this is confined entirely to that single unit cell. It's not shared with any others. Okay, and then if we have an atom at the edge, that is shared by 4 unit cells. Okay, so for example, if we have a compound in which the anion occupies the corners and then the cations at the center, in other words, a body-centered in which the body atom is the cation and the corners represent the anion. Okay, that would be a 1-to-1 ratio of cation to anion. Okay, the other thing, okay, so this is calculating density. Okay, so we have iron, and iron, let's go back. Iron is a face-centered cubic packing arrangement. Okay, so let's go back to our diagram. I'm sorry, it's a body-centered. Sorry about that. It's a body-centered. Okay, so there are two iron atoms per unit cell. Okay, so we have 1/8 of an atom at each one of the corners times 8 corners, and then we have the atom at the center. Okay, so that's 2 iron atoms. That's where they get this. This is Avogadro's number. This is the molar mass, and this is how much the unit cell weighs in grams. Okay, the volume we can find by taking the length of an edge and cubing it, and then converting to centimeters. We take mass divided by volume, we get density. Okay, and this is actually quite close to the accepted value for the density of iron. Okay, the other calculation I wanted to talk about, we go on to Okay, here we have some ionic solids. And starting out with binary salts like sodium chloride. Sodium chloride has crystals which are in a cubic shape. It has a face-centered cubic unit cell. The chlorides are at the corners. The sodium is in the octahedral holes. Zinc sulfide forms what is known as a sphalerite structure. This is a face-centered unit cell for the sulfide, and then the zinc is in the tetrahedral holes. Okay, and then fluoride, calcium fluoride. This is a 1:2 ratio. Calcium ions are in a face-centered cubic unit cell, and then the fluorides are in the tetrahedral holes. That is, each fluoride is in the center of 4 calciums. Okay, the other thing I wanted to show you was calculating the radius. Okay, so we have the edge length here. It's 513 picometers. Okay, so what is the radius of the chloride ion? Okay, so we're given the length. Oops. Back. We're given the length of the lithium chloride unit cell. Okay, so we can find the radius using the Pythagorean theorem. And that comes out to 5.13 times the square root of 2 picometers. Okay, and then so the radius is 181 picometers. Okay, the ratio of the radius of a lithium ion to the radius of a chloride ion is 0.42. Okay, so why did we divide this by 4? Okay, this is the radius of the cell, but then we're just looking at the radius of the lithium. I'm sorry, the radius of the chloride. Okay, and then, so the average ionic radius for chloride ions is 181 picometers. And then, so the structure of lithium chloride is similar to the rock salt structure of sodium chloride. Okay, I'm going to go ahead and stop there.